Hello students. So in this particular episode we will be discussing Gauss Theorem. Before we start with the actual topic, we need to understand these three terms: area vector, electric flux and solid angle. So let's start with area vector. Now we are all aware about area. Area is a two-dimensional thing, and basically area of different geometrical figures, we are aware of their formulas. But here in physics we will discuss area vector. Whenever direction is assigned with an area of a given surface, then that is known as an area vector. Direction means it indicates the orientation of the surface under consideration. I'll give you an example. Suppose this is an irregular shaped ball. Now let us consider its total surface area to be S. Let's consider a small elementary portion like this. This is a small elementary portion. It can be considered to be ds1. It represents small elementary area. Let us consider another small elementary portion. It can be considered to be ds2. Let us consider another one. This can be considered to be ds3. These are the small elementary portions of the area of this given asymmetrical closed surface, right? Now area vector at a point will be represented by drawing a vector in the outward direction. This is the area vector. Point to be noted is that it should be perpendicular to the surface which it represents and should be directed in the outward direction. Over here, the area vector would be like this, perpendicular to the surface which it represents and directed in the outward direction. Here the area vector would be like this, ts3. It's represented by an arrow which is in the outward direction and perpendicular to the surface which it represents. So area vector of a given area is represented by an arrow where the arrowhead represents the orientation of that particular surface. And the point to be noted is that area vector is always perpendicular to the surface which it represents. The length of the arrow that represents the magnitude of the area of the surface under consideration. And the arrowhead represents the orientation of the surface. So this is area vector. So area vector is a vector quantity. It is having both magnitude as well as it represents the orientation of the surface. That is, it also represents direction. Regarding its SI unit, obviously area, its SI unit would be meter square. Now before we proceed to the other topic, let's discuss a simple illustration of this area vector. Suppose a square face of side say 2 meter is lying on the XY plane. So what will be its area vector? So what we have considered is, this is X axis, this is Y axis and this is Z axis. This is a square of side 2 meter and it is lying in the XY plane. This is the area under consideration. We need to represent its area vector. So area vector of this would be perpendicular to this surface and in the outward direction. That is towards Z axis. Z axis is in the outward. All the three are mutually perpendicular to each other, right? So this is the origin. So this would be the area vector. Parallel to Z axis, that is this direction. So this will be the area vector. So in this case, area vector would be represented as magnitude vector is consisting of two parts, magnitude part and then the direction part, isn't it? So magnitude, area of a square, it's side square, so it would be 4. And then its direction, don't forget to mention its direction. As I told you, area vector of a given surface is perpendicular to the surface and in the outward direction. Here the area vector is along the Z axis. Z axis is represented by k cap. This is the unit vector which represents positive Z direction. And unit is obviously meter square. So this is the area vector. I hope you have understood this particular topic. So area vector is a vector quantity and the area of a given surface when represented in the vector form, that is known as an area vector. We'll discuss its significance. Okay. Now, next very important topic is electric flux. Now, you need to understand this particular term, flux. In the subsequent topics, we will discuss magnetic flux, luminous flux. So, if you are aware of this term, flux, then you will be easily able to understand electric flux, magnetic flux, luminous flux. So, basically this term flux is a term associated with the surface. I repeat, flux is a term associated with any given surface, right? Electric flux means we are dealing with a surface held in an electric field, and then the total number of electric lines of force passing through that surface normally means perpendicular to that surface, that represents electric flux. So the electric flux associated with a surface held in an electric field is defined as the total number of field lines crossing that surface normally. Normally means in a direction perpendicular to the surface. Now, since you are aware of electric flux, you can easily define magnetic flux. So the definition is the same. Simply you need to replace electric lines of force with magnetic lines of force. So magnetic flux associated with the surface held in a magnetic field will be defined as total number of magnetic field lines crossing that surface normally. And in a similar way, luminous flux can be defined. It is also associated with the surface through which light energy passes through that surface normally in a direction perpendicular to the given surface. Right? So let's now understand its SI unit and then its mathematical representation. How to quantitatively define this electric flux. So what we do is, we consider any surface. Suppose this is a surface. And this is the electric field. This represents electric field. Now let's consider the surface, total surface of this given, total surface area of this given surface be S. So if you represent a small elementary portion, then its area would be represented by ds. This is the elementary area, right? Just now we discussed area vector. So its area vector would be represented by this. As I told you, area vector of a given portion of a surface is represented by a vector in the outward direction, right? And it is perpendicular to the surface. It is perpendicular to the surface. It makes an angle of 90 degrees. This is perpendicular to the surface. So this is the point. Now, what's the angle between electric field and the area vector? It is angle theta. Suppose it is angle theta. Now what we do is, E vector, which is the electric field vector, it is in the oblique direction, right? So we can resolve it into two mutually perpendicular components. One along the direction of the area vector and the other perpendicular to the area vector. So if you resolve this electric field vector, this we will get E cos theta, while along the surface this component of the electric field will be E sin theta. Now concentrate, or rather recall the definition of the electric flux or the qualitative aspect of the electric flux. As I told you, flux associated with the surface are the total number of field lines crossing through that surface normally, that is in a direction perpendicular to that surface. So here E cos theta, it is the component of the electric field which is crossing perpendicular to this given surface. So it is only this component which contributes towards the electric flux. E sin theta is the component of the electric field which is lying on the surface, not perpendicular to the surface. So this component of electric field won't contribute anything towards the flux associated with this surface. Got it? So basically, flux associated with the surface is represented by phi. Now since we are dealing with small surface area, the small flux associated would be given by E cos theta. This is the component of the electric field which is perpendicular to the surface, and the area, that is ds, area under consideration. So this component of the electric field which is perpendicular to the surface only contributes towards the flux. You can justify the statement by unitary method as well. Through unit area, the electric field lines crossing normally is E cos theta. Through area ds, the flux, which are the number of field lines crossing normally through this area, would be E cos theta multiplied by ds. So this is the expression, right? So it can be also be represented as a scalar product of E vector and ds vector. So in scalar form, it can be represented as scalar product or the dot product of electric field and area vector. This is the scalar product, and theta is the angle between the electric field vector and the area vector. So one more important thing which we conclude is, since flux is given by the scalar or the dot product of two vector quantities, therefore it is itself a scalar quantity. The flux is a scalar quantity having magnitude but no direction, right? So what will be the total flux associated with the entire surface? It may be represented as E vector dot ds vector and the integration of it. So this is the flux. This is the expression for the flux, right? Let's deal with some special cases. Let us consider some special cases. Now what happens is, suppose the surface is lying like this. Its area is considered to be S, and electric field is represented like this, while area vector, it is also along this direction. Both are in the parallel direction. That is, in this case, the entire electric field crosses normally through the surface. So what's the angle between E vector and ds vector? Theta is the angle between E vector and ds vector. Over here, theta is 0 degree. Over here, the angle theta is 0 degree. So, this case 1, when angle theta is equal to 0 degree. Cos 0 is 1. So what do you get? Phi is equal to E ds. So angle between these two is 0. Cos 0 is 1. So we get E cos 0 is 1. Integration ds will give you the total surface area, that is S. So this is a special case. In case all the field lines crosses normally through a given surface, then the flux associated with that surface is numerically equal to the product of the strength of the electric field and the area of the surface under consideration. So we can easily find its SI unit as well from this particular formula. SI unit of electric field is Newton per Coulomb. It's force per unit charge, isn't it? What about area? It's meter square. So this is one of the SI unit. Another unit, you remember, electric field may also be expressed as volt per meter into area. Area is meter square. So we get volt meter. So this is another unit for measuring electric flux. So this is case 1, right? Case 2. If this is the scenario, this is the area vector, which will be always in the outward direction perpendicular to the surface, and this is the direction of the electric field. Let us consider this to be the direction of the electric field. In this case, the entire electric field, the net electric field, is along this surface, which means that electric field is at right angle to the area vector. So here theta is 90 degree, and accordingly what we'll get is cos 90 is 0. So electric field would be equal to 0. So very important point to be noted is that in case the field lines are along this surface, then it won't contribute anything towards the flux. In such a case, the flux would be equal to 0. Third scenario. If we consider, these are the cases of plane surfaces, right? If we consider the case of a closed surface, any closed surface, then flux would be simply given by closed surface integral of the electric field. It will be given by the closed surface integral of the electric field for any closed surface. It will be given by closed surface integral of the electric field. So let us recapitulate this particular topic. Flux is a term associated with a given surface, and electric flux may be defined as the total number of field lines which passes through a given surface in a direction normal to it, right? So electric flux mathematically or quantitatively may be defined as the product of the strength of the electric field and the area vector, provided the field line is crossing normally through the surface. And in an oblique direction, it is given by the scalar product of electric field and area vector. And in case of closed surface, flux is given by closed surface integral of the electric field. So, last one is, we'll discuss solid angle. So, we all are aware of plane angle, isn't it? Plane angle, it's a term associated with two-dimensional plane angle. It's actually defined as in the case of circle, we have defined plane angle. It's defined as the ratio of the length of the arc to the radius of the circle under consideration, isn't it? So solid angle is a term which you use in the case of a closed surface. It's a 3D term, three-dimensional. So solid angle, let's discuss this particular term. Then after all these three topics, we'll be in a position to understand Gauss Theorem more appropriately, right? So solid angle, as I stated, it's a term which we use in 3 dimensions, in the case of a sphere or any other closed surface. Let's consider this to be a sphere. This is a sphere. This is the center. Now let us consider its total area as S. Obviously, if radius is R, then its total surface area would be 4 pi r square. So let us consider a small portion of the sphere. Small portion of the sphere. This may be represented as ds, isn't it? An area vector would be in the outward direction like this. This is the area vector. It would be in the radially outward direction. This is the area vector. Now these are the points on the edges of this elementary portion. If we connect all these points with the center of the sphere, then we'll get a diagram like this. We'll get a diagram like this. So it's in the form of a conical shape like this. It's in a 3D. So this angle subtended the center. This angle subtended the center. This is known as solid angle. Small surface area, the small solid angle is represented by D and like this. This is the symbol for solid angle. Small solid angle. Right? If R is the radius of the sphere, then small solid angle subtended the center of the sphere by the small elementary portion is given by ds vector divided by r square. This is the formula basically for the solid angle, right, in magnitude. This is actually the special case. Solid angle is not only applicable in spherically symmetrical closed surface, it can be used in any 3-dimensional closed surface. I'll illustrate another example. Let us this to be a asymmetrical closed surface. This is the point, and let us consider this to be the small surface ds. Over here, this is the area vector. It can be represented by n cap. So this is r, suppose, the average distance from this point O. Here solid angle is defined as ds vector dot n cap divided by r square. This is a scalar product of n cap. N cap represents the direction, the radially outward direction. Here, n cap and ds vector were parallel. Both were in the radially outward direction. So the angle between these two was 0. So cos 0 is 1, so we will be left with this only. So this is the actual formula for ds. If we represent it in magnitude, then scalar product can be used. ds, its magnitude, multiplied by n cap. The magnitude of unit vector is unity. Angle between these two, cos theta. This is it. This is the general formula of a small solid angle. And the total solid angle subtending the center of a closed surface can be easily obtained by integrating it, by taking suitable limits. So again, if you consider this particular case, it will be much easier to derive the net solid angle in the case of a sphere, which is symmetrical. So total solid angle may be represented by r is constant. It can be represented like this. Closed surface integral. We are talking about a closed surface. Total surface area of a sphere is 4 pi r square. So what do you get is, so total solid angle, it is 4 pi steradian. This is the SI unit of solid angle. SI unit of plane angle is radian. SI unit of solid angle is steradian. So total solid angle, this we have proved for a sphere, spherically symmetrical surface. It can be proved for any asymmetrical surface as well. I am restricting myself in this article, I am not going to derive it, but total plane angle enclosed by a circle or enclosed by any closed loop is always 2 pi radian. In the similar manner, just remember, we have derived as well, the total solid angle subtended at a point inside a closed surface is 4 pi steradian. So here also if we integrate, we can easily mathematically justify this fact. ds cos theta divided by r square, it would be equal to 4 pi steradian. So this is a very important result. I repeat, total solid angle subtended at a point inside a closed surface is 4 pi steradian. So I hope you have understood these topics: area vector, electric flux and solid angle. So students, one thing I would like to mention, if you are really getting benefited from my videos, then do subscribe it and do ask your friends also to subscribe my YouTube channel. Right? I'll be posting the next episode, which is Gauss Theorem. We'll discuss the statement of Gauss Theorem, and as well we can mathematically verify Gauss Theorem. So that's in the next episode.